Hi, welcome to section 7.3 and 7.4 of stoichiometry. Take a pause and work on these 4 warm-up problems and then let's check your answer. Problem 1 says balance the following equation when propane, which is C3H8, combusts. And so combust would be combustion reaction. So we know C3H8 will react with air or burn in air, and it will produce CO2, which is carbon dioxide, and water. And that's always. Always combustion reaction will be the fuel. In this case, it's propane burning in oxygen, always producing CO2 and H2O. In order to balance the equation, we can write out all the elements that we see: carbon, hydrogen, oxygen. And so now we just have to count up how much is on each side. Remember that the left side of the arrow, those are your reactants. And then after the arrow, those are your products. So look at the reactant side. I have 3 carbon, 8 hydrogen, 2 oxygen. On the product side, I have 1 carbon, 2 hydrogen, and 3 oxygen. I'm going to change colors. And so when we are balancing the equation, we are only going to be adding coefficients because we do not want to change the identity of the compound. So first thing I'm going to do is I'm going to balance the carbons. There's 3 on the reactant side, so in order to get 3 on the product side, I'm going to put a 3 as a coefficient in front of CO2. This changes to 3, and then I have to update my oxygen because it's with the carbon. So 3 times 2 is 6, plus my 1 from water. It's going to be 7. Now I'm going to balance my hydrogens. So there's 8 hydrogens on the reactant side and only 2 on the product side. So 4 times 2 will give 8, so I'll put a 4 in front of the water. This will change it to 8, and now I actually have to update my oxygen again. 3 times 2 from your CO2 is 6, plus now your 4 from water. That's going to give 10. Now our carbons and our hydrogens match, but not our oxygen. There's O2 on the reactant side. 10 divided by 2 will be 5, and that's why I'll put a 5 in front of oxygen. And so my balanced equation is 1 propane plus 5 O2 produces 3 CO2 and 4 H2O. The second problem is, what is the molar ratio between propane and water from the equation above? The molar ratio is the coefficients in front of each compound for the balanced equation. And I'm looking for propane. There's no number, so we know it's an invisible 1. To show that we're talking about a ratio, we're going to draw this colon. And then water's coefficient is 4, so the ratio is 1 to 4. Calculate the molar mass of propane. So we know that carbon, there's 3 of them. 12.01, that's the mass from the periodic table, times 3, that's 36.03. Hydrogen, the periodic table's mass is 1.01. There's 8 of those, and you want to add those together, and you'd get 44.11 grams per mole, and that is your molar mass. Now, the last one, we're going to throw all of that wonderful information together. Calculate the moles of water formed from 22 moles of propane. So we're going to start with our 22.0 moles of propane. Draw our wonderful line because we're converting. And this is going to be our molar ratio because we started with moles. So if I have moles of C3H8 at the top, that's what I'm going to automatically put at the bottom. The number is going to come from the balanced equation. Since there's no number in front of propane, it's 1. And then we are going to water. So it's 4 moles of water at the top. Put parentheses around it. We don't need to convert anymore because it's just going for moles of water. Moles of propane will cancel, leaving you with moles of water. 22 times 4 is 88.0 moles of H2O. And that's your answer. Great job. Section 7.3 is mass calculations, and the aim is to learn to relate masses of reactants and products in a chemical equation. So here's a problem. We have 2 aluminum plus 3 iodine produces 2 aluminum iodide. Suppose we have 35 grams of aluminum. What mass of iodine should be weighed out to react exactly with this amount? This problem doesn't have us look at the product yet. We are just looking at the reactants. So we are going to begin with our 35.0 grams of aluminum. In order to get to that molar ratio, we have to go from grams to moles. So I'm going to draw my wonderful line, and I'm going to find aluminum on the periodic table because I know I'm going to go from grams to 1 mole of aluminum. I know it's 1 mole of aluminum because the number I'm going to grab off of the periodic table will automatically mean 1 mole. So aluminum's mass is 26.98, and I only have 1 aluminum because it's just Al. I'm going to change colors. This right here is going to be my molar ratio. And so since I have moles of Al at the top, that's what's going to fall to the bottom, moles of Al. And it's asking how much iodine am I going to have. So I know moles of iodine are going to be at the top. The numbers are from our balanced equation. So 2 for aluminum and 3 for iodine, right? This is our molar ratio. And it's asking what mass of iodine. And so this is going to be grams. I'm not done converting. So I'm going to draw my wonderful line. Moles of iodine, I know are going to drop to the bottom, and I know it'll be 1 mole of I2 because this is the molar mass. So iodine on the periodic table is 126.9, but I have 2 of them. And so I have to multiply it by 2, and I'll get 253.8 grams per mole. So that's why I put 253.8 grams of iodine here at the top. To make sure I actually set this up correctly, I'm going to go through and cross out my units. So whatever I see at the top and at the bottom, they can cancel, like grams of aluminum, moles of iodine. So I know my answer is going to be in grams of iodine. Now the hardest part after this is figuring out how to put this into the wonderful calculator. So if you're not really comfortable doing math with fractions, you can just type it exactly how you see it. So we'd have 35.0 parentheses. Fractions are going to be top divided by bottom. So it's 1 divided by 26.98. And we just keep adding all of them in order to make sure we don't miss any of them. Divided by 1. And then equals, and after you do all that, you'll get something that's like 493.865, 8265, something, and that's what's going to be in your calculator. So if we're rounding to sig figs, we started with 35.0 grams, so that is 3 sig figs, 3 significant figures. So I need to round this to 3 sig figs. So the 4 will count, the 9 and the 3 will count because those are all significant figures, so I draw my line. This 8 will tell that 3 to round up because it's 5 and above, right? So we can round that to 494 grams of iodine. And that's how much we will need to react exactly with 35 grams of aluminum. Now that we know how to do these calculations, you will always need a unit and the compound with the number. Here's the equation from the warm-up, and the question is, what mass of oxygen will be required to react exactly with 96.1 grams of propane? So we will begin with our 96.1 grams of propane. Draw our line because we need to get to moles to get to our molar ratio. So I'm going to put grams of C3H8 here at the bottom and 1 mole of C3H8 at the top. In order to get our molar mass, carbon, the mass of carbon is 12.01. We have 3 of those. 12.01 times 3 is 36.03. Hydrogen's mass off the periodic table is 1.01, and there's 8 of those. And so this is 8.08. When you add them together, you'll get 44.11 grams per mole. Remember, that's just saying for every 1 mole, it's 44.11 grams. I'm going to change colors to show my molar ratio. So I know moles of C3H8 will come down here. because I do want them to cancel. And I'm trying to figure out the mass of oxygen, so I know moles of O2 will be here at the top. The numbers are from our balanced equation, so it's 1 and 5. 1 for propane, 5 for oxygen. And now it's going to ask me to get the mass of oxygen. So I draw my other line. Moles of O2 will be at the bottom, and because it's molar mass, it's going to be 1 mole. Oxygen's mass on the periodic table is 16, and I have 2 of them, so 32.00 grams per mole. 32.0 grams of O2 will be at the top. To make sure I set this up correctly, I can make sure everything cancels, right? So grams of propane, moles of oxygen, leaving me with grams of oxygen. Now remember, if you're not sure how to put this into the calculator, you can type it in how it is, because these are all fractions. So you'll start with 96.1, parentheses, 1 divided by 44.11. Remember, it's always top divided by bottom. 5 divided by 1, and 32.0 divided by 1 equals, and when you put that into the wonderful calculator, you'll probably get something around 348.5830877. And so our starting point was 36.1, and so that is 3 sig figs. If I'm rounding, 3, 4, and 8 are all significant, so I draw my line. This 5 will round that 8 up, and so I can round this to 349 grams of O2. So if I have 96.1 grams of propane, I will need exactly 349 grams of O2 to react with it, so there's nothing left behind. Now we get into 7.4, and this is calculations involving a limiting reactant. And the aim, 1, is to learn to recognize the limiting reactant in a reaction, and 2, to learn to use the limiting reactant to do stoichiometric calculations. Let's talk about s'mores first. So, how many s'mores can you make if you start with 2 graham cracker halves, 6 chocolate squares, and 1 marshmallow? That will be 1 s'more. So let's say this is the recipe to make exactly 1 s'more. What if I gave you 6 graham cracker halves, 18 chocolate squares, and 3 marshmallows? The way I've lined them up, it's very easy to tell we can make 3 wonderful s'mores. Well, what if I gave you 20 graham cracker halves, 60 chocolate squares, and 1 marshmallow? Hopefully you quickly thought you could only make 1 s'more, and that's because you only had 1 marshmallow. There were no more marshmallows to make any more s'mores. And there you have it. You already figured out how to get the limiting reactant. Here's another image. I have 5 hot dogs, 4 hot dog buns, and I have only made 4 hot dogs in a bun and 1 hot dog. So the limiting reactant is the reactant that runs out first in a reaction. It's going to produce the least amount of product. So in this case, the limiting reactant would be the hot dog buns. LR is the limiting reactant. And then the excess, that's what we have left over, right? Like we have this 1 hot dog left over. If I go back to this slide, this was your limiting reactant, and these you had in excess, because the marshmallow limits the amount of s'mores you can make. Now, how do we throw this all together for chemistry? Looking at this problem up here, the chemical equation says nitrogen combines with hydrogen and produces ammonia. Suppose you have 25 kilograms of nitrogen gas and 5 kilograms of hydrogen gas are mixed together and they're reacted to form ammonia. Calculate the mass of ammonia produced when this reaction is run to completion. Most of you will end up writing 1 stoichiometric equation, but you actually have to do 2 because you have to compare how much ammonia is being produced since we have both of our reactants. I am going to begin with 25.0 kilograms of nitrogen gas. The unit is in kilograms, but we need it in grams because we have to convert to moles to get to our molar ratio. kilo means 1,000, so 1 kilogram will be at the bottom, and 1,000 regular grams are at the top. Now that we've converted to grams of nitrogen, I can do the molar mass of nitrogen. I know that grams of nitrogen will be at the bottom because that was what was at the top. And I know since we are doing my molar mass, 1 mole of nitrogen is at the top. Nitrogen on the periodic table is 14.01. I have 2 of them. So this will be 28.02 grams per mole. So that's what I will put here, 28.02. Now that I'm in moles, I know moles will drop to the bottom, so moles of N2. I know a lot of our practice has been from reactant to reactant, but now we are going from reactant to product because we're trying to see how much ammonia is being formed. So I know moles of NH3 will be at the top. The numbers are from the balanced equation, so 1 for nitrogen, 2 for ammonia. And since it's asking calculate the mass of ammonia produced, I know I have to go to grams. So I draw my next line. 1 mole of NH3 will be here at the bottom. And I know grams of NH3 will be at the top. To calculate for that, I know my nitrogen is 14.01. There's only one of them. 14.01. H, that's hydrogen, that's 1.01. And I have 3.03. I need to add these together. I got 17.04, so that's what I'll put up here. And so I'm done converting. In order to make sure I set this up correctly, I can make sure all my units are canceling, right? Whatever's at the top and the bottom, they can cancel out. Grams of nitrogen, or kilograms of nitrogen actually. Now grams of nitrogen, moles of nitrogen, moles of ammonia, leaving me with grams of ammonia. When I put this into the wonderful calculator, I'll get a number that looks like this, 30,406.85225. If I'm rounding to just a whole number, this could round to 30,407 grams of ammonia. If you wanted to round to sig figs instead, I'll write this in a lighter color. 25.0, this is 3 sig figs. And so to round this to 3 sig figs, the 3 counts. This is a captive 0. That 4 will count. That 0 will not round up that 4. So you could say 30,400 grams of NH3, which is ammonia. You think you're done, but you're not done yet. And so now we have to do the same with your 5 kilograms of hydrogen gas. Draw your wonderful line, because remember we have to go from kilograms to regular grams in order to go to moles. So here we can put grams of hydrogen at the bottom and 1 mole of hydrogen at the top, because this is our molar mass. So hydrogen, the mass of 1 is 1.01. There's 2 of them. So this will be 2.02. And now that we're in moles, I know my moles of hydrogen drop to the bottom. And I'm still trying to figure out moles of ammonia. So 3 is what's in front of hydrogen from the balanced equation, and 2 is still in front of ammonia. And once again, we have to convert that to grams. So since moles of ammonia is at the top, I know 1 mole of ammonia will be at the bottom. It's 1 because we are talking about the molar mass. The 17.04 grams of ammonia goes at the top, and we are done converting for this. So again, to make sure we set this up correctly, I can put this over 1, and then anything that's at the top and the bottom will cancel. So kilograms of hydrogen, grams of hydrogen, moles of hydrogen, moles of ammonia. When you put this into the calculator, you'll probably get a number that looks like this, 28,118.81188. If I rounded this to a 1 whole number, I would probably round it to well, I would round it to 28,119 grams of ammonia. If you are doing sig figs, remember this is 3, because these are trailing zeros, they do count. 1, 2, 3. How would this one round that 1? It would round down. So you'd get 28,100 grams of ammonia. So you've done all this wonderful math, but you're not entirely sure how much ammonia is actually produced. So to see how much ammonia is actually produced, you just compare those two numbers. The one that produces less ammonia, that's your limiting reactant, and however ammonia it produces, that's how much you can actually produce. So comparing the 30,400 versus the 28,100, this right here is your theoretical yield of ammonia. So that's how much ammonia could be produced. And it came from our limited reactant. So if I put this into a wonderful sentence to like throw it all together, let me pick a color. We could say the mass of ammonia produced is 28,119 grams. Hydrogen. Oh no, my hydrogen disappeared. We'll just do H2 is the limiting reactant. And nitrogen is the excess reactant. So that's how you would take all that information and figure out which one's the limiting reactant, which one's the excess reactant, and how much is actually produced. Good luck with your homework, and send me an email if you have any questions.